Hi everyone, and welcome to part 2 of our 22nd lecture of CS 2100. So in this lecture, we are going to introduce adjacency matrices, um, which are a way for representing a graph as a matrix. And then we'll show how using adjacency matrices, we can easily compute some interesting results about graphs. Then we'll make again a connection between graphs and relations, and we'll talk about transitivity and connectivity in this context. So let's get started. So what's an adjacency matrix? The adjacency matrix for a D graph with vertices V1, V2 to Vn is a matrix n by n where Mij, meaning entry in row I, column j, is the number of edges from vertex Vi to Vj. And so in an undirected graph, any edge between Vi and Vj increases both entry Mij and entry Mji. So here's an example graph. So let's look at, let's say, Rome, Paris. We can see that there's this number 1 indicating that there is a connection between Rome and Paris. And so on with all the other ones. Let's say Madrid to London. There is no connection with Madrid to London, and therefore we have 0 here. Anyhow, so that's how you build an adjacency matrix. So here is an example problem. We want to give an adjacency matrix for the graph below, and here it is. So if let's look at W to V, W to V, there's 2 edges. Or from X to Z. So X to Z, there is 1 edge, and so on. So this is the adjacency matrix for this graph. So it's really easy to construct adjacency matrices from a graph, and vice versa. Okay. So this is just a gentle reminder of how to do matrix multiplication. So let M be an adjacency matrix, and we want to compute n times n, or m squared. And recall that m squared ij comes from multiplying row I by column j. And how do we multiply them? So we multiply each element in the row with the respective element in the column, and then we add them together. And that's the number that goes in here. And so we continue doing that until we fill up the whole matrix. So this is this gray row with the gray column, and so on. So as it turns out, we can use adjacency matrices to compute some interesting facts about graphs easily by using matrix operations. For example, let M be the adjacency matrix of a graph G. Then entry M Kij counts the number of length K walks from vertex I to vertex J in G, which is a really interesting result. So that allows us to compute walks easily by just doing matrix multiplication. Theorem 1 from chapter 7 also tells us that M1 plus M2 plus Mk is equal to the number of non-trivial walks of length K or less. So if you look at this example graph, and let's, for example, see how many non-trivial walks of length 2 there are between V and W. So there should be only one such walk. Let's look at the graph. Here's V, here's W. And indeed, the only walk of length 2 is this one. And so on. So yeah, the number of walks of length k are really easy to compute using matrix multiplication. And note that matrix multiplication is an operation that is really easy to implement in computers, which is why this is really handy result to know. So here's another example problem. For this graph, we want to give the adjacency matrix M, and we want to compute M squared, and then we want to determine these numbers of walks. And so this graph is much smaller, so this should be much easier to do. So this is our adjacency matrix, M, and this is M squared. And now the question is, how many walks of length 2 exist between B and B? So if we look at M squared, that should give us this number, and it's 5. And then the other question is, how many walks of length 2 or less exist between B and C? 2 or less. So we look B and C, B and C. So we have 0 plus 2, which is going to be equal to 2. Okay. And so here are these results that I just showed. Okay, so this is a nice kind of tractable example problem that shows us how we can use matrices to compute the number of walks. Okay, so let's now make again a connection between graphs and relations. So given the relation R on a set A, we can form the graph AR, meaning the graph of the relation R. And recall G is equal to V comma E, and thus V is equal to A and E is equal to R. So meaning the domain of the relation defines the vertices, and edges, and the relation itself defines the edges. So if this is the relation that is given to us, then we can represent it as a graph like this. So it's going to be a directed graph. For example, BD is an element of the relation, and there is this edge from B to D, and so on. And of course, we can then also write down the adjacency matrix of this relation. Note that the entries for a relation can be only 0 or 1. And that's because we cannot have link from B to D twice. Okay. Now, this is a refresher about compositions of relations. Recall that the composition R, circle R, is the relation on A given by the rule A of C is the element of R, circle R, if and only if there is an element B, element of A, such that AB is in R and BC is in R. So there has to be this element in the middle that connects them. So let G be the graph of R and H be the graph of R, circle R. So then there is an edge from A to C in H, if and only if there are edges from A to B and from B to C in G. Okay. So then let M be the adjacency matrix for R and N be the adjacency matrix for R, circle R. So then NAC is 1, if and only if MAB is 1 and MBC is 1. So this is just restating what we've said here in using this matrix form. Okay. So coming back to Boolean products and how to compute it in the context of matrices, the Boolean product of M with itself, denoted M squared, is computed just like matrix multiplication, except that we replace multiplication with AND and addition with OR. And then M squared is the adjacency matrix of our circle R. So so we can really easily compute the composition of a relation by again using matrix operations. And here is an example. So we have this relation, and these are the here we have the adjacency matrix. When we multiply it with itself, we get M squared, which represents R circle R. You can draw this, and you'll see that this indeed holds. So that's a really easy way to compute the composition of a relation with itself. And this is how the Boolean product of matrices works. So remember, multiplication is AND, addition is OR. It's actually really easy to do this. And the same as before, you're multiplying rows with columns. Okay. So recall that R is transitive. If when AB is element of R and BC is element of R, then AC is also an element of R. So let M be the adjacency matrix for relation R. Then it turns out that R is transitive if and only if M squared is less than or equal to M. Where this less than or equal, it might be a little bit confusing when you apply to matrices. So we have to define it. So M squared less than or equal to M means that for every pair of indices I and J, M squared of ij is less than or equal to mij. So it kind of makes sense. So you have to compare respective pairs of entries in these matrices. So, for example, mij is equal to 1 whenever m2 of ij is equal to 1. So, okay, now the question is the relation of adjacency matrix M transitive. Let's see. So each entries in M squared have to be less than or equal to respective entries in M. So is that true? So 0 is less than or equal to 0. Again, 0 is less than or equal to 0. 1 is less than or equal to 0. That's not true. So this relation is not transitive. And here is why. Because AD is an element of R and DC is an element of R, but AC is not in R. And because the Z is not transitive. So again, this is an example, another example how we can easily compute using matrices. For example, whether a relation is transitive or not. Okay. Then let's look at transitive closure, which is a smaller relation that contains R and is transitive. It's called transitive closure. So here's an example. If A is equal to 1, 2, 3, 4, and we define the relation R using these pairs, then the transitive closure of R is this relation 1, 2, 3, 3, 3, 4, 4, 3, 4, 4. And now another interesting result is that if M is the adjacency matrix for R, then the adjacency matrix for the transitive closure is the following. And here case the length of the longest path in the graph of R. So it's really easy to compute, again, transitive closure relation using matrices. Finally, a note on connectivity. So let G be a simple graph on n vertices with adjacency matrix M. Then G is connected if the following matrix consists of all ones. And so how do we compute this OR between matrices? M or M squared is the matrix whose row I, column j entry is mi plus m squared ij, where we are using Boolean or for plus. And so to verify that G is not connected, we can compute this expression here, and we can see does it have all ones. And so we did this here, and it doesn't have all ones, and therefore it is not connected. So the fact that we have these zeros here implies that the graph is not connected. And so this is it for our lecture 22, which is also the last lecture of this semester that we'll record. Thank you all for watching this, and see you next week.